Hi everyone, this is the final project for CSE 190. In this project, we implemented reinforcement learning. In the lecture, we talk about two primary types of reinforcement learning, which are model-based learning and model-free learning. And today, we are going to implement a typical type of model-free learning, which is Q-learning, where the probabilistic models of the robot is unknown. All you can do is to let the robot try out different actions many times, and based on the reward of each action, come up with the optimal policy in each location. Our goal for this project is to implement Q-learning and compare the resulting policies with the true optimal policies given by Markov decision process, and see how many of our Q-learning processes match the MDP's optimal policies. Let's take a look at how Q-learning works. Each state in the map except the goal, worst, and peaks is divided into 4 parts, representing 4 different actions, either going up, going down, going left, or going right. And each small part is filled with Q values, which is the expected utility from a single state under a single action. And they usually initialize to be 0. To update the Q values, just use the formula shown on the right-hand side. The new Q value of a state under an action is updated depends on the reward of taking that action and the maximal F value we could get from the landing state. Here, the F value is indeed the Q value plus the L value, and the L value represents the exploration incentive for an action from a state. So we choose the function of L to be C, the constant, over a number of times this action has been taken before. On the right-hand side, here's an intermediate video of the Q-value updates when running on a 3x4 map. The algorithm is that the robot starts in a random valid state and keep moving until it reaches the absorbing state. When it chooses an action to move, it will choose the action with the greatest F value by using the formula 2. Notice that since F is Q plus L, so even if at first an action of a state is always chosen because it got the largest Q value, after running many times, the L value of that action will eventually go down and thus motivate the robot to explore the other actions. For example, look at these two states here. At first, they tend to go back and forth between these two states because those two actions here got the largest Q values. But that's fine. After many steps, their L value is going to get down and will try to explore other actions. As you can see here, it's trying to going down. After an action is picked, the robot will then move and tell you the reward of that move. Then you can update the Q value specifically for that action in that state based on Formula 1. Also, we updated the count for that action in order to later calculate the L value in Formula 3. The robot will eventually land in an absorbing state, goal or pit, and would restart another iteration by placing in another random start state again. The iteration would end either the Q values of each iteration converge or reaches a maximum iterations. It takes a while to finish all the iterations and converge. So let's look at our final Q values. Here's our final Q values. For each state, we will then choose the action that has the largest Q value to be the optimal policy of each state. And you can see that each chosen action, specifically the one near the goal, the value of it is updated close to the reward you could get from the goal. Also, we generate the optimal policy in order to compare it with MDP. So on the left-hand side is the policy that run by MDP, and on the right-hand side is the policy that run by Q-learning. For a 3x4 map, as you can see, it perfectly matches. And now let's take a look at a larger map. Since the intermediate video for such large map is really long, so I'll just show you the final updated Q value. And let's get its policy and compare it with MDP. Here again, on the left-hand side is the policy that run by MDP, and on the right-hand side is the policy that run by Q-learning. After comparing, we find that some states' policies are different, which are circled out on red. So in such a 10x10 map, we got around 85% accuracy, a little bit worse than the smaller map. The reason why this happened might be because with Q-learning, it takes longer than MDP to converge. Since we use the same mass iteration for both Q-learning and MDP, and we stop at most mass iteration loops, it is likely that Q-learning does not fully converge while MDP does. So we think that this error rate is permissible. And that's it. Thank you for watching.